Okay, so we want to find friction along the hill. If you're sledding down it, let's think about this. We have friction pushing up the hill. You have your weight pulling down, straight down, and only a part of that weight, right? So I'm going to break this into some components here, parallel to the hill, perpendicular to the hill and parallel to the hill. So part of this force, part of that weight, is pulling you into the hill, and the normal force is pushing you back up. There's our normal force, right? Part of the weight is being used to actually pull you down the hill, and that's what we're interested in. I called that weight parallel in the write-up, and I guess we can call this weight perpendicular, because it's not really x and y, or x and y is kind of tilted in this way, or tilted that way. So we want to know what that is, because if we can look at this, if from the displacement equation, you've already calculated your acceleration, because we have the length of the hill, the displacement that you went, and we have the time that you spent on that hill, time it took to do. So we already have the acceleration. And if we go back to Newton's second law, net force is equal to mass times acceleration. Well, we weighed the sledder and the sled at the beginning, so we can calculate the mass, we can calculate the acceleration, and that means we can find a net force. But we're not done, because that net force, let's see, the normal force and the perpendicular weight, those are going to cancel out or balance each other anyway. So the net force I'm left with is really, let's see, F net equals the weight that's parallel, that component of the weight, minus how much friction there is. And that's what we want. Friction's our goal in the end. So if we can figure out what component of the weight is pulling it parallel to the hill, and we can find the net force, well, then we can find the friction, which is what we want to do. Okay, so last question, how do we figure out that parallel component? Okay, so think back. We knew the angle of this hill. We measured that, right? So this angle right here is the same as this angle right here, because geometry. That discussion is for another video. Suffice it to say, those angles are the same as we look at it. So this component of the weight that's parallel is really the opposite side of that triangle right now. So when you think opposite and you think triangle, this should trigger some trigger some trig in your mind. You see what I did there? Sine of that angle is opposite over hypotenuse, right? In this case, the opposite side is that parallel component. That's what we want. And the hypotenuse is the original weight, the original force that's pulling it down. So sine of the angle, that's just a number. We know the weight. We can solve this equation for that parallel component. So the weight parallel to the hill, at least the part of it, the component that's pulling it down the hill, is going to be the full weight times the sine of the angle that that hill makes with the ground. Cool. So let's recap. We know that the parallel component of the weight is pulling it down the hill. We know that we can find that by taking the full weight times the sine of the angle, if we have that, we can plug that into here, because we can solve for net force by doing the mass times acceleration. Acceleration we found from that equation right there, the displacement equation. So with net force and with the parallel component of the weight, we can solve for friction, which is our whole goal in the end.